So, thanks to all. Greetings from behalf of the Daedalus Science Study team. Alex, thank you very much for this excellent introduction. So, to set the scene, in this image, we see the different layers of the atmosphere defined by the temperature, their temperature gradient. And right away from this image, one can identify a key transition region in the atmosphere, which is the lower thermosphere. And in particular, altitude ranges between 100 and 200 kilometers. Here, the color scale swaps out to view more detail further up. And zooming out, we can see that temperatures in the thermosphere increase with altitude due to EUV radiation, and together with the EUV radiation, an additional source of energy comes from the solar wind, transferred via the magnetosphere, as seen here, by mechanisms that are not well understood. And in particular, during times of very large solar and geomagnetic activity, for example, during solar storms, coronal mass ejections, this input increases substantially and can be the single largest energy source in this region. And here in this movie, it's noted that the lower thermosphere up to 500 kilometers is exaggerated. So in this plot, we see the range of temperatures and its variation during quiet and active times, and together with temperature, which changes drastically, particularly in this 100 to 200 kilometer range. So do neutrals. The neutral constituents are shown in the middle plot, which show the largest gradients in density versus altitude. And also on the right-hand side plot, the ion species, which show large variability. And at the same time, within this region is where a key transition happens, essentially the transition from atmosphere to space. And above this region, charged gases and electrodynamics dominate. It's a collisionless regime where molecules break up into atoms by UV radiation. Gases stratify by weight, whereas below 100 kilometers is where neutral gas dynamics dominate. It's a collisional regime. Molecules and atoms mix by turbulence, and composition does not depend on molecular weight. So it's in between this transition region where the atmosphere meets space, or to define it better, where the neutral atmosphere meets electromagnetic forcing. In this animation, together with the temperatures that we saw earlier, also electron density and neutral winds are plotted as a function of pressure level in the thermosphere. And this is before and during a geomagnetic storm event, as shown here with the identified by the AE index, following fast-moving coronal mass ejection that hit the Earth's magnetic field. And whereas initially solar UV radiation dominates, right now intense variations are observed at high latitudes, causing traveling disturbances, moving to lower latitudes, and longitude-dependent variability. And these effects are caused by particle precipitation from the magnetosphere and also by Joule or ohmic heating due to huge mega-ampere currents that are closing within the ionosphere, together with waves, tides, and gravity waves from below. So in the next slide, this flowchart summarizes the processes that are related to Daedalus science, and in particular, the processes that Daedalus will directly observe are marked in red. On the top, beyond solar radiation, the main energy sources into the thermosphere are Joule heating driven by currents, particle precipitation, and further to the left, together with the heating processes, variability in the thermosphere-ionosphere is caused by atmospheric waves, gravity waves, planetary waves that are poorly characterized. thermosphere and ionospheric variability caused either by these heating sources or by dynamics. They have significant effects and consequences down to Earth, as shown in the lower layers here. And finally, energetic particles from outer space impinging onto the atmosphere, they cause considerable chemical changes impacting odd nitrogen and the odd nitrogen cycle, which is critical to ozone down below. These processes are described in the Daedalus mission objectives in terms of energetics, dynamics, and chemistry. And Daedalus will pursue specific questions on these areas. In this figure, it's shown how it is exactly within this region between 100 and 200 kilometers that key processes happen. Field line currents shown here flowing along the Earth's magnetic fields. They close through this 100 to 200 kilometer range, and doing so, they produce large amounts of heat in the form of Joule heating, as ions within this region collide with neutral species. And shown in this oversimplifying schematic is an example of Joule heating occurring within this region, which is of course much more complex and undersampled, and the underlying principles and processes are largely unknown. Moving further on, energetic particles gyrating about the Earth's magnetic fields, they precipitate within this 100 to 200 kilometer transition region, depositing energy and producing short-lived HOX and NOx, odd hydrogen, and much more long-lived odd nitrogen, NOx. So to quantify and understand these processes, there's a need of measurements right within this region. And whereas field line currents and precipitation has been sampled extensively by past missions at higher altitudes, to quantify and understand these processes, there's a need for in situ measurements right within this region, within the region where both Joule heating and particle precipitation maximize. Further on, to summarize the mission objectives, as shown also in the figure on the right, key science questions related to energetics are how and to what extent Joule heating and particle precipitation deposit energy in the lower thermosphere-ionosphere. What is the local response in the lower thermosphere-ionosphere to Joule heating and particle precipitation, energization, and ionization? And what's the variability of collision, cross-sections, and frequencies, and the resulting conductivity with altitude and varying conditions? Science questions related to dynamics and variability are: what are the relative contributions of solar, magnetospheric, and atmospheric forcing influencing the lower thermosphere-ionosphere fluid dynamics and electrodynamics? What are the amplitudes and spectra of small-scale gravity waves and their propagation characteristics? How do large shears, sharp gradients, and small-scale instabilities develop? And related to chemistry and regional climate, what are the effects of particle precipitation on composition, on ion chemistry reactions, and the polar NO reservoir? How are energetic particles characterized in terms of spectra, energy spectra, gradients, and flux distributions? And what's the morphology and the characteristics of the LTI as an upper boundary condition for improving existing general circulation models? These mission objectives are related to a number of derived products that Daedalus will be targeting. And on the left, we see products that include the main heating sources on the top, estimated in situ by direct observation of all key parameters involved in these derived products of Daedalus. And in particular, this includes the cross comparison of various estimation methodologies for Joule heating, ohmic heating, and frictional heating. And Daedalus will enable testing all three methods against each other. And the corresponding geophysical observables that are involved and that are needed for these calculations are listed on the table on the right-hand side in terms of ionospheric, ionized parameters, thermosphere parameters or neutral parameters, and then fields and energetic particles in the bottom. And Daedalus will also measure in situ currents, conductivities, ion neutral cross-sections, and collision frequencies, all of which are critical unknown parameters and all of which are involved in the heating and dynamic processes of the lower thermosphere and ionosphere. Until now, some of these geophysical observables that we listed in the previous slide and some of the derived products such as Joule heating and conductivity have been derived in situ only in this region via measurements made by sounding rockets. Even though there has not been a complete, comprehensive set of all the measurements needed. For example, neutral composition is often assumed via models. And in addition, sounding rockets by nature only cross through this region in a snapshot. They give an instantaneous profile of these processes and at certain locations over the launch site. So they cannot generally provide information on the latitudinal extent or on the temporal evolution of these key processes. Compared to that, Daedalus will perform measurements of all key parameters involved that were listed below. And then in the lower panels, we show some examples of passes by Daedalus over the regions where these processes maximize. In the middle panels, we show the altitude-latitude profile of these processes, including of examples of how Daedalus would sample these processes, seen in these black lines across the altitude-latitude profiles. And this shows an example of how Daedalus will enable the determination of the latitudinal extent and sampling at different altitude along orbit. And then at the top panels, the corresponding time series of this sampling, in situ sampling by Daedalus, and the derived products is shown. So this gives a movie of the sequence of events and how Daedalus will enable revisiting this area and giving an estimate of this, the evolution of these processes. So to briefly show the measurement concept, measurements in this altitude range in the 100 to 200 region for a prolonged time can only be done via elliptical orbits. Simulations show that a perigee of 140 kilometers is feasible for a prolonged mission duration, and a 3-year duration is identified as a threshold. And measurements below that altitude can be performed by descents, perigee descents by use of propulsion. What is shown here is that elliptical orbits lead to perigee and local time precession. Perigee is shown here with the green arrow. And these actually enable the global coverage and the coverage of different regions, different latitudes and different local times in the Earth. And an example of a coverage plot is shown here on the right. So this local time precession is actually a key benefit of Daedalus. And closing, I'd like to mention that at the same time, whereas these single satellite in situ measurements are extremely valuable, dual satellites are also investigated for the Daedalus mission concept, subject, of course, to various constraints, such as rocket fairing and budgetary constraints. And between a multitude of dual spacecraft configurations, an altitudinal separation, as shown in this figure, was considered key to Daedalus objectives. And this is an example of a dual spacecraft configuration with an altitudinal separation right when Daedalus moves over the perigee of interest at high latitudes. This altitudinal separation would enable sampling of these key processes at 2 different altitudes, giving an estimate of the altitudinal extent, as shown here with the 2 different spacecraft crossing through the latitudes and altitudes of interest. So to summarize, the quest for Daedalus is to explore this atmosphere-space transition region, and Daedalus will do that by providing unique and unprecedented measurements with a comprehensive suite of instruments. The aim is to better understand the atmosphere-space connections that play out there. And by that, Daedalus will close important and missing links in the coupled Earth system. And the path to science closure is to establish sufficient coverage of the relevant regions at the necessary scales and with sufficient performance, which is currently investigated. And these are main topics of the ongoing science and also the ongoing system studies. So to summarize, Daedalus aims to improve our understanding of the energetic and dynamics of the atmosphere-space transition region and the lower thermosphere and ionosphere, and of the neutral plasma interactions that affect them. And while we are at the logos page of the Daedalus Science Study Institutes, Therese Jørgensen will introduce the rest of the session and the scope of the workshop in relation also to the Daedalus mission objectives. So thank you very much. With that, I will pass the floor to Therese.
Yes, thank you, Theodoros. Here's Therese Moretto-Jørgensen from Bergen. And I, together with my co-organizers of the session, is a member of this science study team for Daedalus, which actually, as you see here, counts 31 scientists from 23 institutions all across Europe, Canada, and the US. And we've been working with Theodoros over the last year already to focus, justify, and thereby define a really solid and exciting science case for Daedalus. And what Theodoros presented here was a brief summary of this work so far. So as we're doing this work, we certainly rely on the knowledge and enthusiasm and engagement from the entire community, maybe even several communities, as this combine atmospheric science and space physics. Without that, we will not be successful, either in this initial selection for Daedalus or taking Daedalus further beyond that. So therefore, it's really great that so many of you have tuned in and joined us for this now virtual workshop. So we really need your help as the entire science community to fully explore what is the scientific value of making these in situ measurements in the lower thermosphere-ionosphere that Daedalus would provide, and also to make sure that we understand the grand challenge science questions that this mission would allow us to address, or that we need these measurements to address. So this is basically the aim with this workshop, is to engage with all of you in this task. As to set us off on this course and then give us inspiration for what hopefully will be a really lively and active discussion, we are extremely happy that we were able to enlist an impressive list of invited speakers that you will hear from next, giving talks about subjects within the lower thermosphere ionosphere science that cover a wide spectrum of the different topics that Theodoros already introduced to you. So we're really happy to go more in depth with all of that. But we also would really invite you to not just listen, but also to give us comments, ask questions, and to please engage with us even beyond this session to help us work further on making a really strong science case for Daedalus, to help us make it happen, basically. So back to Claudia, and we can listen to some nice talks.
Yes, so thanks a lot, Therese, and everybody for this very good introduction.